So we have a 5 kilogram object that's sitting on a plane down here that's inclined at 60 degrees to the horizontal. Now that 5 kilogram object is not moving anywhere, and the question simply is, what is the force of friction on that object? If it's not moving anywhere, what is the force of friction on that object? Well, we need to first have a look at what forces are even acting on that object. I know that there's the acceleration due to gravity acting on the object, so there's a force called weight happening. Now, gravity is actually happening vertically downwards, isn't it? That way. And the force of gravity is 9.8 metres per second times the mass, which is 5 kilograms. I'll just explain that. We know that force equals mass times acceleration. We've got a 5 kilogram mass, and gravity is 9.8, so it's 5 times 9.8, 49. Now, it's 49 kilograms metres per second minus 2 like that, or it's 49 newtons that's acting in that direction. (49 newtons acting in that direction. So, as in the last lesson, we want to resolve that purple vector into components in appropriate directions, and at right angles is a good idea. So I'm going to declare going down the plane to be my x-axis. That direction there is going to be my x-axis, and I'm going to declare going perpendicular to that to be my y-axis. So I'm going to resolve that purple vector into vectors in the x and y directions. Now remember that the y-axis can actually head down here as well, and the x-axis is not just heading out that way, but it's also heading out that way. But I'm going to resolve it into those two directions. Now, I just wanted to point out that the force of gravity is actually pulling straight down here, but it can be resolved in that direction and in that direction. So those two green arrows are the arrows where I'm going to, well, they're the vectors that I'm going to find, which are the purple vector that's been projected in the x direction and in the y direction. And they're at right angles to each other. Because this force of gravity, the weight, is pulling straight downwards, but the inclined plane is in the way, so it's not moving downwards. And it's part of it is pulling straight that way, but the inclined plane is pushing it back up that way with a reaction force. And part of this purple vector is pulling down that way, but the friction force of the plane is pushing back that way, and so the object is not moving. Right, I want to know what's going down in that red or that x direction. So The weight is 49 newtons. What I've just written there is referring to the amount of that weight of 49 newtons that is heading down that inclined plane. How much of W, the purple vector, is heading down in the x direction. So I'm multiplying the vector W. I'm doing the dot product of the vector W and the unit vector I, the unit vector in the x direction. And then I'm using I as a direction finder to make it a vector in that direction. Now we know that the dot product of W and I like that is written as the size of I and the size of W multiplied together, and cos of the angle between them. And then, of course, we've got that I at the end there. How big is I? That's right, it's a unit vector. It's 1 unit. So this is actually the size of W cos theta in the x direction, which is why I've got the unit vector I. The size of W is 49 newtons. Now the angle between the purple vector and that red x-axis, what's that angle? That's 60 degrees in there. That's gravity coming down there. We want to know what is the angle between that direction and that direction from our diagram, between the red and the purple as such. Well, if that's 90 degrees there, then that would have to be 30. So it's 49 times cos of 30 degrees times I to give it direction. 49 times cos of 30. All right, so it's 49 root 3 on 2, or about 42.44 in the I direction. So there's 49 newtons pulling straight down, the force of gravity acting on that 5 kilogram block. If you resolve it into going down the plane and perpendicular to the plane, there is 42.44 newtons pulling down the plane. And we could calculate how much was pulling that way as well. But we're only after the force of friction, and the force of friction is counteracting that one there. So the force of friction is acting back up the plane. The force of friction is acting exactly opposite to the force we just found, to the vector we just found. Which means the answer is, what's the force of friction acting on that 5 kilogram block that's not moving, it's sitting on an inclined plane at 60 degrees to the horizontal? The friction is 42.44 newtons. And what is its direction? It's acting up the plane. That's what the force of friction is that's happening here. And just as a matter of discussion, this vector acting in this direction at right angles here, that's what gravity is, but pulling at right angles to the plane. It's exactly counteracted by this normal force, this reaction force perpendicular to the plane. Sometimes the piece of wood or whatever might bend a bit, I guess, but in this case, those forces are cancelling each other out. The object's not moving, and therefore, if these forces cancel each other out, it must be friction that's stopping it pull that way with 42.44 newtons. A couple of things that were mentioned here. A newton. I used the conversion that a newton is just 1 kilogram metre per second squared. These are multiplying. The kilogram is multiplying with the metre per second squared. It's not kilograms per metre per second squared. It's kilogram metres per second squared. It's a newton, which is a measure of force. A couple of other words that were mentioned. Mass. Now, mass is what's called a scalar quantity, and I wanted to just point out a couple of quantities like that. So as we've encountered so far in this topic on vectors, we have two types of quantities, scalars and vectors. Scalars are the ones that have magnitude, that is, size, but no direction, particularly at a given point. Vectors are the ones that have size and direction. Now this makes sense. We're drawing arrows pointing in the direction that the particular vector is acting. So some examples of things that are scalar might be mass, which is what that 5 kilogram object was. It's just 5 kilograms. It doesn't act in any way, but as soon as the force of gravity acts upon it, we now have a force that we call weight, and that weight is acting, well, in this case, downwards towards the centre of the Earth. So mass itself is scalar, but mass acted upon by the force of gravity, mass times acceleration, is a force which we call weight. And weight has direction, but mass doesn't. Something like charge, in chemistry or physics, you might be looking at the charge of different particles and so on. Something like volume. These have size but don't have direction. And some words we have to be careful with. Distance. Distance is scalar, but displacement is about, I guess, location relative to some origin. And so you could be in a certain direction from that origin, whereas distance is just an amount of length. A good analogy there might be this morning when I drove from my driveway to school, I might have driven 5 kilometres, and this afternoon I will drive 5 kilometres to get back to my driveway. So my total distance will be 10 kilometres. If I park in exactly the same spot in the driveway in the evening, then my displacement for the day will be 0. So distance, speed. Temperature is an interesting one. People think it has positives and negatives, but just purely at a point, it has no direction. Whereas weight, displacement, velocity, acceleration, these all act in a certain direction. Of course, all these ideas about a force like weight, force is just an acceleration acting on a mass, and weight is just a word for that, where the acceleration is due to the Earth, for example. So that was just a couple of things to point out. Thank you.